Good afternoon, and thank you for joining us for the fourth webinar in the series of Offshore Wind series, Learning from the Experts. I'm Andrew Zielinski, an advisor with NYSERDA's large-scale renewable team. It is my pleasure to be joined by today's guest, Johannes Pfeifenberger, with the Brattle Group, who will be giving a presentation on offshore wind transmission systems. Before I introduce our speaker, a few reminders for participants and some background on the webinar series. Next slide, please. Firstly, if you're experiencing any technical issues, please contact Sal Gravin at the email at the bottom of this slide. The webinar series is being recorded, and the recordings and presentation slides for all webinars in this Learning from the Expert series will be available on NYSERDA's website at the address as well on this slide. All participants have been muted. We will have time for Q&A following the presentation, so please use the Q&A function to submit your questions for the speaker. Next slide, please. New York State is working to advance responsible and cost-effective development of at least 9,000 megawatts of offshore wind by 2035. Offshore wind is a critical component in achieving the state's goal of 70% renewable sources of electricity by 2030 and 100% zero-emission electricity by 2040. Relevant to today's webinar series on offshore wind transmission series, the National Offshore Wind Research and Development Consortium has recently awarded 5 projects in this area. To learn more, visit the consortium's website. While offshore wind has been providing clean energy to other parts of the world for several decades, the industry is brand new to New Yorkers. To provide interested stakeholders and members of the public with accessible, impartial information and opportunities for engagement on specific topics of interest, NYSERDA is hosting this educational webinar series called Learning from the Experts to connect the public with independent experts in key topics in offshore wind. We endeavor to select learning from the expert speakers based on their expertise, not necessarily for alignment of opinions with NYSERDA or the state of New York. If you would like to suggest a topic for or speaker for future webinars, you can email us at offshorewind@nyserda.ny.gov. Please note the views and opinions expressed in the presentation are those of the presenter and the presenter only. Next slide, please. It is now with my pleasure to introduce our speaker, Johannes Pfeifenberger, a principal at the Brattle Group. Johannes is an economist with background in electrical engineering and over 25 years of experience in the wholesale power market, design renewable energy, electricity storage, and transmission. He specializes in transmission and wholesale power markets. He is also a senior fellow at Boston University's Institute of Sustainable Energy, a visiting scholar at MIT's Center of Energy and Environmental Policy Research, and serves as an advisor to research initiatives by the Lawrence Berkeley National Laboratories, Energy Analysis and Environmental Impacts Division, and the U.S. Department of Energy's DOE Grid Modernization Lab Consortium. Thank you, and now I'll hand things over to Johannes.
Thank you so much, Andrew. Can you hear me okay?
We can hear you fine.
Great. Let me share my screen. Right. Well, thank you so much for joining. I hope you had a good lunch and this won't put you to sleep. Transmission options for offshore wind. Obviously, the power from these wind turbines that you see on this picture here has to come to shore somewhere, and once you're on shore, you have to get it to the load centers as well. So that does require transmission. I'm going to give you a little bit of background in the next half hour on just offshore wind commitments that we're dealing with and the New York context, and then let's do a deep dive into offshore wind transmission itself, the configurations, the trade-off between individual gen ties versus a planned offshore grid, some case studies, New Jersey, UK, New England, and New York, of course, and a few thoughts on risk mitigation before we close with the takeaways. I love this picture because it really puts the size of these wind turbines in scale. But more importantly, the technological progress has been tremendous. This picture is a couple of years old, and we are already installing 12 megawatt turbines right now. The first large-scale offshore wind project was just approved yesterday, Vineyard Wind, and they are using this 12 megawatt GE turbine. But you know, that won't be the end of it. 15 megawatt turbines are already being marketed, and as shown on this slide, ARPA-E is exploring 50 megawatt turbines. And that scale is really reducing the cost of offshore wind and making it more attractive as a renewable resource. In terms of the US, we're quite a bit behind Europe and China. Those are the biggest regions for offshore wind development, but we have committed in New England, New York, and the Mid-Atlantic states about 30,000 megawatts of offshore wind. And we've contracted, as you see in this table, 4,300 in New York, about 4,200 in the Mid-Atlantic states, and about 3,100 in New England. But we also know that these 30,000 megawatts just won't be the end of it. Based on decarbonization pathway studies in various regions, we think, for example, that New York might actually need well north of 10,000 megawatts of offshore wind by 2040, certainly by 2050. New England, the same, where on-land resources seem to be more limited in terms of permitting. We have estimated that New England alone might need about 25 to 40,000 megawatts by 2050, which includes decarbonizing transportation and home heating through electricity. New York has been very proactive. Just in January, the PSC and NYSERDA completed the initial report on the New York Power Grid study. That study looks at the transmission infrastructure needs, both at the utility level, that's the local transmission and distribution needs, within each of these bubbles that you see on this chart, an offshore wind integration study that explored how to best get 9,000 megawatts of offshore wind, the current New York commitment, into the state's grid. And then there was a zero emission study that put it all together with respect to bulk transmission to figure out how much generation and storage is needed to get the state to 70% renewables by 2030 and zero emissions by 2040. And what you see here is that the 9,000 megawatts really only have one way or two ways to come into the state, either through Long Island or by routing the offshore wind directly into the New York City area, as you see at the bottom of this chart. Just to give you a scale or a sense of how offshore wind fits into the likely resource need, what you see on this chart is that by 2040, the state will have to add about 10,000 to 15,000 megawatts each of onshore wind, offshore wind, solar, and storage to make it all work, to make a zero emission grid work. This is adding more capacity to the state's grid than is currently installed on the grid. So the next 2 decades will fundamentally change not only the resource mix the state is using for electricity, but with that change in resource mix, obviously you will have transmission needs. And the Power Grid study explored those needs. The good news is the state has been very proactive with bulk power upgrades. There will have to be a fair number of local transmission upgrades to accommodate onshore wind and onshore solar. And beyond 2035 or so, there might need to be additional projects beyond the ones that are currently underway. As you may know, the state has 3 large bulk power projects currently underway in Western New York, in Central New York, and in Northern New York. And those bulk transmission upgrades go a long way towards making all this possible. So let's go into offshore wind, and you will be able to ask questions once I'm through this. What will a cost-effective offshore wind transmission solution look like for the state? But it's really, New York is not there by itself. Some of the contracted offshore wind plants that New York has already committed to are located off the coast of Massachusetts, for example, and there are new lease areas under development that are still uncertain, but it's really an East Coast and Northern, Mid-Atlantic and Northeastern wind industry. As you can see on the small map in here, the wind is actually much better in the northern part of the East Coast than in the southern part. And these wind commitments that you see on this map reflect that. But to get these wind plants connected to shore, you really have several transmission needs. One is what's shown as the yellow line here, the submarine link to shore. But once you are on the beach, so to speak, you still need a onshore link to the existing grid. The strong part of the existing grids are not usually right at the shore, so there might be 10, 20 miles of onshore links to reach the stronger part of the existing grid. And third, as shown in green here, the onshore grid will have to be upgraded to accommodate all the new generation injection. The grid is just not strong enough to take in all the offshore wind that would be generated. And the situation is very different in different parts of the US. New York, with having New York City right at the coast, has some very strong grid infrastructure right there. But other places like southern New Jersey don't have much of an existing infrastructure that would be close to shore and capable of integrating the necessary amount of wind. So to plan how to, building the submarine cable to shore is the easy part, but then to integrate that into the existing grid requires transmission planning. The existing grid operators have a process called generation interconnection process that works reasonably well for one plant at a time. But the challenge is that once you exhaust the capability of the existing grid, the next generator making this interconnection request might be faced with $1 billion or $2 billion of upgrades. So you hit a wall through that generation interconnection request where the upgrades become so expensive that not a single generator can pay for them. And that's where you need the ISO's regional planning process to kick in to create a more wholesale solution for the amount of wind generation that is needed. And that magnitude exceeds the scale of individual wind farms. So generally, these processes are not very well developed yet. The exception is New York. Several years ago, New York implemented its public policy transmission planning process, and that really has become a model for the rest of the country in its ability to address these public policy considerations fairly expeditiously and cost effectively. Of course, the onshore grid planners don't have much experience with the offshore part of the transmission facilities. and developing an offshore grid for 30,000 megawatts of wind generation from, New Jersey or Virginia to Massachusetts is really a challenge in terms of doing that cost effectively, which also requires a precisely phased-in plan that aligns the timing of the transmission expenditures with the generation development. You certainly don't want to be late with the transmission and have a wind plant wait a year before it can interconnect. At the same time, you don't want to spend all that money years ahead of when wind generators would be interconnecting. So those are the challenges with the planning process, and these are really challenges related to the onshore planning. Now, there are different concepts of how to get offshore wind to shore. One is just using radial generation tie lines for one plant at a time and just connect them to the existing grid. That's what has been used so far. It works well for the first several plants. It becomes more complicated once the ability of the onshore grid to accommodate these gen ties is challenged. In several places, like in Europe, you have shared collector stations where the tie line that comes in is sized much larger to a scale where you need several wind plants to fill this. This is attractive for longer distances and cases where you don't have a lot of landing points. So you want to consolidate offshore wind and then bring a larger tie line to shore. And then we got these meshed grids. One can have individual tie lines, and to increase the reliability of these tie lines in case one of them goes out, one could mesh them together offshore and create a more flexible, more reliable way to bring offshore wind to shore. And then lastly, there's a backbone grid where you create basically a loop offshore into which several wind plants can be connected. Doing, the options at the bottom here, of course, does mitigate environmental impact because you have fewer landing points. And it might also reduce the cost of the onshore upgrades, as I will show you in just a moment. Here's an example. PJM, the system operator just south of New York, is currently undertaking a solicitation of offshore wind transmission solutions for the state of New Jersey. New Jersey has committed to 7,500 megawatts of offshore wind. And PJM, the system operator, is bidding out transmission solutions to integrate those 7,500 megawatts. The responses that folks can bid in include these onshore upgrades, the transmission to the shore, and then the transmission to offshore, and also the option to connect the offshore wind farms through a backbone or sort of more local meshes. The first bids are supposed to be submitted by the end of the summer, so this is happening very quickly. The benefits of using gen ties is really that you can get up to speed very quickly, do a contract. The contract for the wind farm is bundled with the transmission solution. And, if you have wind farms that are 400 to 800 megawatts, that's how you can get started. And that's what the first few contracts look like. That works reasonably well, maybe up to 40 miles from shore. But as you scale up to like 9,000 megawatts, to take 9,000 megawatts to shore with individual 400 megawatt cables would be a lot of landing points. So you change technology. You can use HVDC circuits that can carry up to maybe 1600 megawatts to shore, but then you get into challenges where planning interconnection points and planning sequences and planning meshing several of these large transmission lines together to increase their reliability becomes important. And that's really where offshore grids, even offshore grids that take individual large chain ties and mesh them together later, have significant advantages. We'll talk more about some of that later. But what we found, it depends a bit on the geography, but a planned approach can really reduce the cost of the onshore upgrades because you can pre-select landing points that are best suited to the onshore, to use the maximum capabilities of the onshore grids. By having a plan to switch to larger procurements that can use HVDC lines, you reduce losses, the transmission losses of moving the power from the wind farm that might be 60 miles away to the shore. And by planning to use larger transmission lines, you also have less impact on fisheries, the environment, you have fewer shore crossings. And if you bid it out separately, you might actually be able to increase competition for the transmission build. And then what folks have found in Europe, if you pre-build transmission, you actually get a more competitive solicitation for wind generation because not every wind generator has to worry about permitting the transmission line all the way to shore. The initial New York Power Grid study found that if you plan to get 5,000 to 7,000 megawatts into New York City, that would be the ideal because the less you land on Long Island, the fewer onshore upgrades would be required. As I mentioned, Europe is ahead on this. The UK grid operator, National Grid, a subsidiary of the National Grid in New York, has undertaken this study, and they found that an integrated approach that uses, as you can see, these meshed high-capacity HVDC lines could reduce total transmission costs by about 19% and cut the number of landing points and shoreline permitting challenges in half. They also found, because the UK is ramping up offshore wind more quickly than any place in the US does so far, they are planning 18,000 megawatts of new offshore wind by 2030 and 40,000 megawatts by for the next 2 decades. If planning the transmission grid starts now, you can achieve these savings, but delaying the planning process by only 5 years reduces the benefit of the planned grid by half. And that is because the more of these smaller individual chain ties you build, the less opportunity you have to plan bigger solutions. We found something very similar in New England, for example, where if you connected New England has committed about 8,400 megawatts, or has about 8,400 megawatts that we think could reasonably be brought to shore from those lease areas. If you use individual chain ties, you really have a sort of spaghetti bowl of cables coming to shore. And these red areas show you that connecting offshore wind to the nearest points on the existing grid creates these overloads on the existing grid. If you do some more planning and scale up procurements of individual wind farms that are large enough so you can switch to HVDC lines that carry more power, and you plan to connect these HVDC lines into, say, the Boston area rather than Cape Cod, then you can avoid most of these onshore upgrades. So just knowing that these savings exist might actually help you get there by making individual procurements sizable enough to support HVDC solutions, and then maybe do a procurement where you pay more for the delivered power, but get them into parts of the grid like the Boston area that later avoid these expensive onshore upgrades. And what we found is, despite the fact that you spend about $2 billion more on the offshore lines, these HVDC lines are more expensive, you make more than up for it by reducing the onshore upgrades with cost savings in that right picture of about $500 million compared to the left picture. But it's not just about money, it's also environmental impacts, and the risk of building the onshore upgrades is actually pretty high, because it's very hard to build new transmission onshore in these states. This just shows you what that onshore upgrade would have to look like. And just getting the next 3,600 megawatts into the New England grid would require about $1.7 billion in onshore upgrades. Now, this is more than a single generator can pay for, so that's why a joint planned solution would make a lot more sense than doing these upgrades one generator at a time. So a few moments on NYSERDA's offshore wind integration study that was done as one of the elements of the power grid study. This offshore wind study assessed the bulk transmission needs of getting the 9,000 megawatts of offshore wind integrated into the New York grid. And it was a very thorough study that included an onshore assessment to assess the interconnection points that are capable of absorbing the offshore wind generation. It had also identified the onshore upgrades. And what the study found is, by putting the wind generation into the right locations onshore and combining those onshore locations with storage, for example, you can actually get most of this done without bulk transmission upgrades beyond what the state is already doing. It also includes an offshore build-out scenario, figuring out which wind areas might become available to the state and how to get that power to shore. And then it included a preliminary permitting and feasibility study of, can you actually get these cables permitted? One challenge, for example, is getting new transmission cables into the New York Harbor. And this study showed that there would be about 25 infrastructure crossing where the new cable would cross the existing tunnels and existing energy infrastructure and telecommunications infrastructure, and you have to route it around shipping channels and so on. The findings of this study for New York are quite positive. Integrating these 9,000 megawatts of offshore wind is feasible without major bulk transmission upgrades, but only if you can route 5,000 to 7,000 megawatts of that offshore wind into the New York City area, because the onshore grid in New York City is much stronger than the onshore grid on Long Island. So that leaves only about 2,000 to 4,000 megawatts to be injected into the Long Island grid, which the grid can handle more or less. I mean, there will be upgrades and further studies will be necessary to confirm these findings, but generally a good outcome. But as you can also see, this is the planning that we're talking about. If you do plan for this and you plan in a way that so you can actually get, say, 6,000 megawatts of offshore wind into the New York City area, you can do that. If that doesn't happen and you interconnect more on Long Island than the Long Island grid can handle, or you plan it in a way that you foreclose an opportunity to get more into the New York City area, then you're talking about potentially very expensive upgrades to the grid on Long Island. But the routing and battery deployment and getting to the right substations is clearly quite important. The offshore wind study also found that to achieve this, you're using very large capacity HVDC lines of 1,200, 1,300, 1,400 megawatts per cable. And to increase the reliability of and guard against the possibility that one of these cables has a month-long outage, it is good to create the options to mesh these tie lines together in the future so they can back each other up. And that's the meshed grid option that we had discussed previously. The challenge in New York, as you all know, of course, is how do you get into New York City? You have to get through the Narrows, and then you have to navigate a very constrained space in the inner harbor of New York. And then, of course, you also have to connect on Manhattan somewhere. So you're talking about real estate, you're talking about connections to existing substations that may not have enough space to accommodate new switchgear and so on. So it is very challenging. And one of the recommendations of the Power Grid study is to coordinate this permitting challenges more actively by getting all the permitting agencies involved, getting Con Ed and the local utilities involved to make sure this can be done. Because if you don't use the space well, you run out of cable routes that are feasible coming into the harbor. And of course, the Long Island shoreline has many environmental constraints and exclusion areas. So you really want to have a plan and maybe pre-permit some of these approach routes. We did, last year, we did a similar study with Barrick and got to very similar conclusions that using individual HVDC lines is just not going to be feasible, because unless you use high capacity lines that can actually get you into New York City, you end up connecting a lot to Long Island, which would trigger major upgrades to the onshore grid. If you use fewer higher capacity cables and route as many as you can into the New York City area, you can actually get to a lower cost, more reliable, more environmentally feasible and permittable outcome. And connecting these cables through a mesh, through an offshore mesh, then can increase reliability and have other benefits. This is an actual picture from the offshore wind study. And what you see here is that you really get as much as you can into New York City, but you can see the constraints here is really challenging. And if you don't build every one of these cables very carefully, you might actually preclude subsequent cables from being feasible. The study then explored meshing the offshore grid together and found that at very modest incremental cost, you can actually increase the reliability of that kind of solution. But one thing I want to point out is there's significant uncertainty of how to best do that. And it turns out one of the bids that NYSERDA provisionally accepted in January from the wind areas off the coast of Massachusetts actually is coming in through the Long Island Sound into Queens. So if you bid these things out folks will find innovative solutions that are not necessarily obvious before you see them. The interesting thing about the meshed grid is that one could also expand this meshing to these wind farms that connect into Long Island, and then the offshore mesh creates a new path between Long Island and New York City, because that link between Long Island and New York City is also quite weak, and the state has already started to address that by soliciting another cable between Long Island and the mainland. But once you have this, you could also mesh a wind farm serving New York with a wind farm serving Massachusetts, and theoretically you could create a new link between Boston and New York City that way. But it does require that these offshore substations are built in a way that would allow them to be later meshed into other wind farms. So risk mitigation, whenever you try to build transmission separate from generation, there's something called project on project risk. The wind developers have been very keen to build their own transmission, so they control the schedule, they control the project risk, they can make sure the transmission is built in synchronous with the offshore wind generation. As long as you can easily connect to the onshore grid, that works pretty well. You can size up projects to 1200 megawatts or 1400 megawatts and get the larger technology cables. But once the low-hanging onshore interconnection points are utilized, and you have significant risks of how to get the onshore upgrades done, then a planned grid has just big advantages, because planning the onshore upgrades for the full scale of the procurement, the 9,000 megawatts in New York and the 30,000 megawatts for the East Coast, for example, gets you to lower cost grid solutions that can actually be built. It's very hard to get to that same endpoint with sort of one Band-Aid onshore upgrade at a time. And if you do use gen-ties initially, it does make sense to build in the options, not only that these gen-ties are large enough to use HVDC technologies so they can be meshed together, but also they are constructed in a way so they can actually be meshed together. So, takeaways. We've calculated that the 30,000 megawatts of committed offshore wind in the mid-Atlantic and northeastern US will require about 1,500 to 3,000 miles of offshore transmission. Just to get that to shore, we're not even talking about the onshore upgrades now. If you do that with HVDC technologies, where every cable has 400 megawatts, you would need up to 75 different landing points. So that is very challenging from a permitting perspective, environmental impact perspective, and 3,000 miles obviously disrupt the sea floor much more than a planned grid that utilizes higher capacity cables. With new HVDC lines, you can reduce that to about 25 landing points and about 1,500 miles of offshore transmission cable. We've pretty much talked about the advantages of planning an offshore wind strategy that utilizes larger scale offshore wind plants, larger scale cables, and increased reliability of using those larger cables by meshing them together. But it's not a one versus the other. I think there's really a hybrid approach that is emerging, and that is go ahead and procure the first few wind farms with individual gen-ties, but do it such that these gen-ties can later be integrated into a meshed offshore grid. that itself requires planning, and that itself is planning, even if you're not creating a offshore grid right away. Finally, I'd like to leave you with some thoughts on the longer term as the states and the federal government increase clean energy targets and increase shares of renewable generation. A more robust interregional grid will become necessary. And why is that? Well, it's really because you need a grid that's larger than the size of large weather systems. If all of the Northeast is in a snowstorm for 5 days, you really want a grid to expand beyond that weather system. You've seen what happened in Texas in February. Texas is not interconnected much with the rest of the grid, and they had severe outages, even though the renewable shares weren't the problem, but you can see what weather can do to generation. So we might end up by 2040 maybe with a more robust national grid, and as you see on the right here, possibly a meshed offshore grid that links wind farms from the Carolinas to Maine, and by linking those wind farms together, that offshore grid would actually be reinforcing the existing onshore grid. So let me stop here and hand it back to Andrew. Thank you so much.
Thank you, Johannes. Please remember, if you have any questions, to submit through the Q&A, and we will do our best to ask as many questions to Johannes as we have time for today. Let's see. Johannes, a question came in. Is the offshore wind developer typically responsible for the tie to the offshore transmission? And if not, or if so, who pays for it?
Yeah, good question. So far, the way offshore wind has been procured in the US, the offshore wind generation developer is also responsible for building the transmission to shore, and the cost of that transmission to shore, which is about 25 to 30% of the total project cost, is part of the contract for the offshore wind. So it's a bundled contract under which both the generation and the transmission to shore is built by the developer and paid for by the off-taker.
Thank you for answering that. Could we go back to slide 20? This question is referencing slide 20. And the question is, how large are typical transmission losses for these long generator leads, and how would a planned system affect those losses? And then further, would an AC or a DC technology affect that? And is there a limit to the capacity or distance for either technology? It's a loaded question, I apologize.
Yeah, no, but it's a very good question. The AC technology has the advantage it's cheaper. Sometimes it has the advantage that it's smaller scale, so you don't need a huge wind plant to fill it. But the AC cables are incurring a lot of losses, and you can only get to, say, 40 miles distance or something like that. There are tricks where you can use intermittent substations to, prop up some of the voltage on these cables to go to longer distances. But AC is relatively inexpensive, but has high losses. I don't have the numbers off the top of my head, maybe 15% or something like that. And it's actually technologically limited how far you can transport the power. If you use HVDC lines, those losses are down to maybe only 5%, and they're largely independent of the distance or much less dependent on distance. So you can go hundreds of miles with HVDC cables, which you wouldn't be able to do with HVAC at all. And this last procurement that NYSERDA made from Beacon Wind Project, I've actually drawn that in as one of those black lines. I think that is using HVDC because it's a long distance going from south of Martha's Vineyard all the way into Queens. So HVDC is more expensive because you need HVDC converters on either side of the cable. And for 2 converters, you pay almost $1 billion just for the 2 converters and then the cable itself.
Thank you. I know you had a slide regarding the planned approach and the mitigation factors for the risk on risk. This is kind of regarding that. It's what is the greatest concern of using a link system? Is it the risk on risk, or is it something else?
Well, the biggest concerns are with a backbone system, not necessarily a mesh system. A mesh system, you can reduce the risk by building individual gen ties and later meshing them together. But if you have a backbone system where you have to build the entire loop before you can interconnect any one of the wind farms, then the question becomes, can that transmission solution that's built by a different company than the companies that build the wind farms, will that transmission solution be completed in time? The answer is yes, that can be done. It requires strong incentives and the right contracts and so on. But you will also hear that the first couple times that has been tried in Europe, the first time in particular, there were major delays, and the wind farms were ready for about a year before the transmission could be completed. And that is the scary scenario for any wind developer or for any off-taker if you have to pay for the wind, but you can't get it to shore. So I think a meshed grid where you build individual gen ties and later mesh them together is actually a way to mitigate some of that. But whenever you have one company build transmission and the other company build the generation, there's a coordination challenge. And that's what the wind developers are concerned about. If they can control every aspect of their project, including the transmission to shore, that's their preference. But it turns out that's not the only challenge, because after you interconnect the first few wind farms, you are hitting a wall with the onshore upgrades where it could take 10 years to plan and complete some of these onshore upgrades. And that's why you really need to think ahead.
Thank you for replying to that and the designation between mesh versus a network approach. The next question is regarding the states basically has, the storage requirements moving forward, and how would those storage goals impact the need for transmission effect of basically reducing transmission for Long Island and New York City in particular?
Yeah, the state's goals are much smaller than the amount of storage that the power grid study found would be needed by 2040. The power grid study found it would be optimal to have about 15,000 megawatts of battery storage on the grid throughout New York. And the idea of putting storage into the right locations is, as you know, wind is intermittent, that if the wind blows really hard and you have a lot of power coming to shore, you can buffer how much the onshore grid has to absorb by putting a battery there. So with the spikes of production, you can charge the battery rather than curtailing the wind, because the takeaway capability of the grid isn't that high. So by putting storage in the right location, you can actually reduce the need for larger upgrades to the onshore grid. But coordinating that, of course, it has its own challenge. How do you do a procurement for storage that is for the right locations in the right substation to work with onshore grid? And one of the recommendations of the Power Grid study is for the state to keep evolving the planning process so that these coordination challenges can be addressed more effectively.
Thank you. That's, yeah, really important to note the Power Grid study had way more storage, than the goals. So the next question is, could you talk about cost for mesh or a backbone system and how they could be shared among ISOs or across neighbors as they may be interconnected among each other?
I think that interregional transmission question and cost allocation will definitely be another seminar at some point in the future. The reality is there are no processes that work or that exist for the most part. The individual system operators try to coordinate, but if they don't have to coordinate, that is their great preference. And it's hard enough in multi-state ISOs like PJM to do cost sharing between different states. Like one thing that's happening now with New Jersey is the state agreement approach only works because New Jersey is committed to pay for 100% of the needed upgrade. But then, of course, New Jersey doesn't want other states to use the facilities that they've just been paid for. And when it comes to interconnecting neighboring regions, like interconnecting a New Jersey GenTie with a New York GenTie to create new links between New York and New Jersey or between New England and New York, you get a lot of people very nervous whether these costs can be allocated correctly, whether New York would be free riding on New Jersey infrastructure or vice versa. So I think we will need these connections ultimately, but we don't have a transmission planning and cost sharing process in place that would make it feasible today. And that's why nobody's even talking about it in terms of actionable items. If you look at the New York Power Grid study, it pretty much treats New York as an island and is avoiding having to deal with these complicated coordination questions with neighbors.
Sure. So our next question is in reference to how the power would be controlled in a mesh system. Would it be basically HVDC? Would it be PARS? Would it be some other controllable device?
Yeah, if you use HVDC lines in all but one of the connections, you can perfectly control where the power flows because the converters that you have on either end of the HVDC lines, they actually control power flows just like a valve on a garden hose. If you have AC lines, it's more free flowing and you could use phase angle regulators and things like that to control power flows. But I don't think that's very practical. I think if you want to do an offshore mesh network or a backbone, you really need to use HVDC because you want to get to that scale, that size anyway. HVDC cables have big advantages, and one of the advantages you can control. What you see on this chart here that's still up is that those green lines are HVDC lines, and the offshore mesh, so AC mesh, they're AC cable links. But because you can perfectly control power flowing on each of the green lines, you can use that to also control how much power will flow on those purple AC lines. And even if you were to connect the upper left portion of that HC 1310, if you connect that to E600, you could still perfectly control the power flows by virtue of using the HVDC lines.
Thank you. So our next question is, should New York State consider a man-made island in New York Harbor to house basically the HVD/AC power transfer stations for multiple projects, if space is such a serious issue in New York City as it is?
That is a very good question. In Europe, several countries are building man-made islands to house a lot of that equipment and consolidate a lot of wind, and then use very high capacity cables to connect to shore. I'm not sure there's space in New York Harbor to build a man-made island. The power grid study, the offshore wind portion of it, has in fact looked at real estate, and so you might land it in one place on the coast that has available space, and then use a cable that goes under the streets, for example, to some place else. I'm not sure that a man-made island would be a good solution for the state, but one could explore that. One thing I want to say is that part of the power grid study, Con Ed has actually proposed to create offshore wind hubs. They wouldn't be man-made islands, but they would be basically creating interconnection hubs where the cables could come in, interconnect, and then Con Ed could make sure that from those hubs you can actually get into the right places of the onshore grid, which is very complicated in a place like Manhattan, because these substations have very limited space and it's very hard to get new cables into them.
Thank you. As we're approaching the end of this, I have one more question, and then we'll wrap it up. What do you think is the federal government's role, if it has one, in RTO and ISO coordination?
Well, that role is very big. First of all, Federal Energy Regulatory Commission does regulate the ISOs and their planning processes. So to the extent the planning processes are not quite up to snuff for facilitating this clean energy future, FERC will have to improve or force the regional grid operators to improve their internal planning processes. And then it's called interregional planning. It was kind of talked about in a FERC order called FERC Order 1000 a decade ago, but it really hasn't worked. So FERC will have to probably look at interregional planning again and find a way to facilitate or make more feasible the coordination between the individual system operators. But the federal government, of course, also has very important roles with sort of offshore wind leases and BOEM, and creating some certainty both with respect to where the lease areas will be that New York can utilize, and permit the transmission cables that will have to come to shore.
Thank you, Johannes, for all your expertise in answering all these questions. Could we go to the closing slide? Yep. And then thank you, everyone, for joining us for this Learning from the Experts webinar with Johannes. A reminder that the webinar recording and presentation slides will be available on NYSERDA's website. Our next webinar in the series is on May 26th, and it's presented by Duncan Solowski with Tetra Tech, who will be describing the submarine cables that bring energy generated by offshore wind turbines to shore, and discuss technical considerations in cable designs and planning. You can register for this webinar and future webinars through our events page at wind.ny.gov. Thank you.
Thank you all.